Assalamu alaikum dear students. I welcome you to the 20th lecture of probability and stochastic processes. So far we have been analyzing a pair of continuous random variables through mathematical processing of their joint PDF, which is a surface of possibly varying height defined over a region or the whole of xy plane. The two continuous random variables in question can assume their values independent of each other without one influencing the value of the other. If that's the case, then the two random variables are called independent and we can analyze their joint behavior in a much simpler manner because their joint PDF can be separated into two functions where one involves only the parameter related to one random variable and the other function involves the parameter related to the other random variable. If the two random variables are not independent of each other, if they influence each other, then we can measure their mutual influence by finding their correlation or covariance, or a normalized measure that we defined last time, which is called correlation coefficient. Today we are going to find these quantities for a few pairs of continuous random variables. It's interesting to note that you can find correlation of two independent random variables, but this exercise is a wastage of time because if the two random variables are independent of each other, then their correlation is just multiplication of their expected values. In other words, the correlation, which is expected value of x times y, is equal to expected value of x multiplied with expected value of y. So it's only meaningful to talk about correlation, covariance and correlation coefficient of two random variables if they are not independent of each other. Today we are going to find these parameters for a few pairs. So let's start with a pair of continuous random variables that we encountered in previous lecture. We are not going to start with that simple pair of random variables which were defined through a flat PDF defined over a rectangular region where sides were parallel to the coordinate axis, because we know in such a case the two random variables are independent of each other. Their correlation is simply multiplication of their expected values and their covariance is 0, so is correlation coefficient. So we are not going to work with any pair of independent random variables. So we are only going to talk about pairs of random variables where the elements of the pair, the two random variables, are dependent on each other. Before we do that, let's have a quick look at the formulas that we are going to use to find correlation, covariance and correlation coefficient. As you can see on the slide, the correlation between two random variables is a weighted average of the multiplication of the values attained by two random variables. So it is integration over the whole xy plane or the extent of plane over which the two random variables are defined, and the integration is for the joint PDF multiplied with value of x and multiplied with value of y. So it is a weighted average of the values attained by two random variables. The covariance is similar with one difference, that instead of using the actual values of the two random variables, we use modified values, and modification is just by subtraction of the mean values of two random variables from the values that we are going to use. In other words, covariance is a joint centralized expected value, where instead of using x and y multiplying with the joint PDF, we use x minus mu x multiplied with y minus mu y and then multiplied with the joint PDF. So covariance is for the centralized random variables where the mean value has been subtracted, or the transformed random variables where transformation is through subtraction of the mean value to make the new transformed random variable a zero mean. So if the two random variables are zero mean, then correlation and covariance are same. But if they are not, we subtract the mean values and get an unbiased covariance which subtracts the mean values of the two random variables. Once we have found the covariance, we can again normalize it with the standard deviation of the two random variables to get a numerical measure, normalized numerical measure, which tells us how the two random variables are going to influence each other, and this normalized measure is called correlation coefficient, and this always lies between -1 and 1. So if covariance or correlation coefficient is a large positive number, then it implies that in that integration where we evaluated the covariance, there were certain pairs of values which were contributing more towards the integral than the other values. So if we get a large positive value as the outcome of covariance, then it means that the values of random variable x and y were more likely to be positive positive or negative negative, because in this case two positive values or two negative values multiplied together then multiplied with the PDF, which is always positive, gives us a positive contribution. So if covariance is positive, then it is more likely for the two random variables to attain values in tandem. That is, if one is positive, that is one is large value, then the other is more likely to attain a large value. Or if one is very small value, the other is also going to attain smaller value. It's more likely for the other to attain a smaller value. And if the covariance is a negative number, then it means that if one variable attains a large value, larger than its mean value, then the other is going to attain a smaller value, smaller than its mean, and other way around also. So in this case, covariance is going to be a negative quantity. Let's talk about a real life situation where a random experiment is performed, two values are observed, and they are related to each other in such a way that if one value is large, the other is more likely to be a large value. Suppose you stand outside a university, and once a student enters the university, you ask him two questions. What is his height and what is his waist? These two quantities are going to be random. They are going to lie in their certain range. The height is going to lie between say 1.2 meters and 2.1 meters, and the waist is going to lie between say 28 inches and 39 inches. So if these are the extents of the values that these two observations are going to take on, then these two observations are not independent of each other. They are going to influence each other. If a person is tall, it is more likely for him to have a large waist measure, and similarly, if the person is shorter in height, then it is more likely for him to have a smaller waist measure. Of course, there will be exceptions. It is possible that a student who is shorter in height has a large waist measurement, and a student who is very tall but very thin and has a very small waist measure. But in general, a taller person has other body dimensions larger, and a taller person is going to have a larger waist measure and a smaller person is going to have a smaller waist measure. Let's move on to our academic problem, where we are going to treat two random variables x and y which are not independent of each other, and then we are going to find the correlation, covariance and correlation coefficient of the two random variables. As I said, we cannot take two random variables which are independent of each other because it's meaningless to talk about their covariance and correlation coefficient. They are 0. So the first pair of random variables that we are going to take will be defined over a smaller region of xy plane, which is 10 by 10. So x extent is from 0 to 10 and y extent is from 0 to 10. So this is 10 by 10 region of xy plane where the PDF is defined. On this square region of xy plane, the PDF cannot be flat, because we know if the PDF is flat over a square or rectangular region with sides parallel to coordinate axis, then it implies that the two random variables are independent. We are going to define a PDF which is a tilted plane. It is not flat, it is a tilted plane with varying height over this 10 by 10 region. We have already encountered this non-flat PDF in previous lecture, so we are going to look at this again. If you see the slide on your screen, then you can see that the PDF for this case is 2x plus y whole divided by 1500. This is the PDF which is defined over this 10 by 10 region, and this captures the behavior of these two random variables x and y. In last lecture, we found the marginal densities of random variable x and y, which were obtained through integration of the joint non-flat density along x and y axes. The two marginal densities are shown on your slide. So marginal density of x is 2x plus 5 whole divided by 150, and marginal density of y is y plus 10 whole divided by 150. These densities are defined for x extent which starts from 0 and ends at 10, and the marginal density of y is also defined for y extent which starts at 0 and ends at 10. If you use these marginal densities to find the expected values of random variable x and y, you can certainly do so. It's very simple, and the values that you get for mu x, that is expected value of random variable x, is 55 over 9, and expected value of y is 50 over 9. Now you can find the correlation of x and y by using the formula that you saw on the previous slide, and when you put the appropriate values of joint PDF and the extent over which the integration needs to be performed and all the other required elements, and simplify the double integration, the correlation between random variable x and y comes out to be 100 over 3. We know that this is a non-flat PDF defined over a square region, so the two random variables are not independent of each other, and the correlation cannot be equal to multiplication of two expected values. The multiplication of two expected values, 55 over 9 and 50 over 9, gives us a numerical value of 33.95, which is not equal to the value of the correlation that we get, which is 100 over 3 or 33.333. So this is confirmed that correlation is not equal to the multiplication of two expected values of random variables x and y. Let's find the standard deviations of the two random variables x and y, which can be found from the marginal densities of x and y. So if you find the standard deviations, the standard deviation of x comes out to be square root of 575 over 81 or 2.66. Whereas standard deviation of random variable y comes out to be square root of 650 over 81 or 2.83. Remember, when you are finding standard deviation, you first find variance, and variance is second centralized moment of any random variable. So to find variance, you take the random variable and subtract its mean value, and then you multiply it with itself, and then take the weighted average with the PDF. The correlation for this particular case comes out to be 33.333, which is a large positive number, because the region over which the random variables x and y take on their values is in the first quadrant. It is a subset of first quadrant, so x and y always take on positive values, and when you multiply these two positive values and the PDF, which is also always positive, you get a function which is always positive, and when you integrate this function over a 10 by 10 region of xy plane, you are going to get a large positive value. Now suppose if we had another pair of random variables whose joint PDF was exactly like the joint PDF we just analyzed, but shifted further away from the origin, but in the first quadrant, then what is going to happen? That the random variables are going to attain larger values compared to the previous case, and the correlation is going to be even higher. Let's do that. Let's shift this joint PDF, which is defined from x is equal to 0 to 10 and y is equal to 0 to 10, to a point away from the origin where now x varies from 2 to 12 and y varies from 3 to 13. So the point where it was origin has moved to a point 2, 3. So the whole PDF has been shifted by 2 units along positive x-axis and 3 units along positive y-axis. You can see this shifted PDF in your slide, and for this shifted PDF you can find the marginal densities, you can find the correlation and other quantities, and they have all been listed in the slide. The joint PDF has a new expression which is derived from the old expression by changing x to x minus 2 and y to y minus 3. So the new expression is 2 times x minus 2 plus y minus 3 whole divided by 1500. And as you can see on the slide, the new expressions for marginal PDFs for random variable x and y are 2x plus 1 divided by 150 and y plus 7 divided by 150. Using these marginal densities, you can find the mean values of random variables x and y, and they are shown on your slide as 73 over 9 and 77 over 9. As expected, these mean values are higher because the whole joint PDF has been shifted some distance towards positive x-axis and some distance towards positive y-axis. So the values attained by the two random variables x and y are higher compared to the previous case. So the average value, the mean value of x and y have also increased. You can find the correlation of the two random variables x and y for this joint PDF, and if you put in the right expression and the right values, this comes out to be 619 divided by 9. In previous case, where the joint PDF was defined over a 10 by 10 region which started from origin and ended at 10, 10, the correlation was 100 over 3 or 300 over 9. If you multiply the numerator and denominator by 3, you get 300 over 9. And in this case, when the whole joint PDF has been shifted, the correlation comes out to be 619/9, which is larger than 300/9. Similarly, the mean value of x and y also have increased, which is as expected. Let's find the standard deviations of random variable x and y for this case. As you should have guessed, the standard deviations of random variable x and random variable y are going to be the same as they were for the previous case, because standard deviation is square root of second centralized moment. When you are finding a centralized moment, you don't use the value of the random variable, but you subtract from it its expected value. Even though in this case the joint PDF has shifted, the mean values of x and y has increased, but when you are trying to find variance, you are going to subtract these higher expected values, higher values of mean from the values of random variable, and this is going to negate this shifting effect. So if you have a random variable x and you get a new random variable x dash from it through a simple shift, the standard deviation of the two random variables are going to be the same. So for this case, the standard deviation of x is again going to be 575/81 whole square root, which is 2.66, and standard deviation of random variable y is going to be square root of 650/81 or 2.83. Let's move on and find the correlation and covariance of our next pair of random variables, which are also not independent, and their joint PDF is shown on the slide. This joint PDF is obtained from the previous PDF that we were discussing, the non-flat tilted plane type PDF, but now this PDF is shifted in the opposite direction. In the first case, the PDF was defined for x values from 0 to 10 and y values from 0 to 10. Then we shifted the PDF away from the origin into first quadrant, and then x varied from 2 to 12 and y varied from 3 to 13. In this case, we are going to shift the whole PDF towards the third quadrant in such a way that shift for x is minus of the mean value of x, and shift for y is minus of mean value of y. So the leftmost corner is going to be at minus mu x comma minus mu y. So this is a point where the origin has been shifted. So this shifted PDF now occupies all four quadrants. Some part is in first quadrant, there are parts in second and fourth quadrant, and there is some part in the third quadrant. To highlight this, as you can see on the slide, I have divided this joint PDF by cutting it into four regions, and these cuts are along the x-axis and along the y-axis. So you can clearly see there are four regions of this joint PDF. These four regions are in the four quadrants of xy plane. This shift of the joint PDF has resulted in two new random variables. Now this joint PDF is for two random variables x dash and y dash, where x dash is x minus mu x and y dash is y minus mu y. It is easy to observe that these two new random variables x dash and y dash are zero mean, because that is how the shifted random variables have their mean also shifted. So if you shift it in the negative direction, then the mean is going to be the mean of the old random variable minus the shift, which is exactly equal to the mean value. So these two random variables x dash and y dash are zero mean random variables. Hence, we are going to find the correlation and this correlation is going to be exactly equal to covariance. So in correlation, we take these values of random variables wherever they are defined, multiply them with the PDF and take the integration of the whole result over the whole region over which the joint PDF is defined. As you can see, when the two random variables x dash and y dash take on values in first quadrant, both values are positive, their multiplication is positive, and you get to multiply this positive number with the joint PDF, which is this tilted plane, and the result is positive. Hence, I have put a positive mark on the region of joint PDF, which is in the first quadrant. Similarly, when the two random variables take on values which are both negative, that is, the values in the third quadrant, both negative values give a positive number, and when this positive number gets multiplied with the PDF, which is always positive, you get a positive contribution. So in the integration of covariance, which is same as integration of correlation for this case, because the two random variables x dash and y dash are zero mean, these two regions give positive contribution, and the region of quadrant 2 and quadrant 4, they give negative contribution. So net result of this whole integration is that you take the two positive contributions and subtract two negative contributions to get the final value. And if you evaluate this integral properly, you will get the correlation, which is same as covariance for this case, to be minus 50 over 81. It's a negative number, a small negative number. And this small negative number gives us a hint that the two negative contributions are more than the two positive contributions. And if you look carefully on the tilted plane shifted in all the quadrants, you will see that indeed the negative areas are going to contribute slightly more than the two positive areas. And if you want to find the correlation coefficient for this case, you have to divide this covariance number minus 50 over 81 with standard deviation of x and standard deviation of y. I'm not going to do that. I'm going to leave this as an exercise for you. It's not necessary to shift a joint PDF towards origin so that it is shifted by a negative value of mean of x in the minus x direction and negative value of mean value of random variable y in the minus y direction. So it's not necessary to bring the point mu x comma yx to origin. You can leave the joint density where it is and then imagine that you have cut that joint density using two cuts which are parallel to coordinate axes and pass through x is equal to mu x and y is equal to mu y. In the slide that you can see now, I have done this to original joint PDF which was defined over a region from 0 to 10 times 0 to 10. As you can see on the slide, the joint PDF has been cut into 4 parts, and the point where these two cuts meet is exactly the point which is mu x comma mu y. So the two cuts that were used to divide the joint PDF into 4 parts were parallel to the coordinate axis. The cut which was parallel to y-axis passed at point which is x is equal to mu x, and the cut which is parallel to x-axis pass through point which is y is equal to mu y. So they two meet at mu x comma mu y, and this is a point where the two mean values are defined. Now these 4 partitions of joint PDF are again marked with 2 positive regions and 2 negative regions. The 2 positive regions are those regions where either the values attained by 2 random variables are both larger than their respective mean values, or both are smaller than their respective mean values. Similarly, the two regions marked with negative signs represent those regions of joint PDF where one variable takes a value which is larger than its mean value, but the other variable takes on a value which is smaller than its mean value. For this particular case, the joint PDF is divided into 4 regions. 2 regions contribute positively and 2 regions contribute negatively towards the evaluation of covariance. And as you can see, the covariance comes out to be a negative number minus 50/81 because the contributions of 2 negative parts is slightly dominant than the contribution of 2 positive parts. In other cases that we are going to consider today, we are going to use this methodology where we will not shift the joint PDF, we'll keep the joint PDF where it is and divide it into 4 regions by cutting it through the point mu x comma mu y using 2 cuts which are parallel to the coordinate axis. The partitioned joint distribution gives you a visual clue as to the final value of the covariance. If the total sand in the 2 positive region is more than the total sand in the 2 negative region, then the covariance is going to be a positive number. And if the sand in the 2 negative regions is more than the sands in the 2 positive regions, then the covariance is going to be a negative number. We are going to use this strategy to analyze the next pair of random variables which are shown in your slide. This slide is for a pair of random variables x and y with a joint PDF which is given by 5x minus 2y plus 20 whole divided by 3500. This joint PDF has already been analyzed and we have found the marginal densities and other quantities for this joint PDF. As you can see from the surface plot of this joint PDF, this is higher in the third quadrant compared to the second quadrant. So the contribution of this third quadrant is more compared to the second quadrant. But the contribution of the first quadrant is more than the contribution of the fourth quadrant, but the things are going to cancel each other and we are going to get a small value. The small value of covariance that we are going to get comes out to be 250/441. So in previous case, the covariance was a small negative number and in this case it's a small positive number. The numbers are small because when you cut the joint PDF with 2 cuts which are parallel to coordinate axes and passing through the expected values of x and y, you get 4 regions with substantial amount of the PDF, the substantial amount of the terrain, the volume of the terrain that the PDF represents. So things do cancel out each other and we get small values of the covariance. Let's look at the next example that we analyzed a few lectures ago. The example is of a flat PDF but not defined on a rectangular region with sides parallel to coordinate axis, but defined over a diamond-shaped region or a square region rotated 45 degrees. So for this diamond-shaped region with a flat joint PDF, we found the marginal densities which were triangular in shape going from 0 to 5 in a rising slope and from 5 to 10 on a falling slope with a peak value of 0.2. So using these marginal densities, you can find the mean values of 2 random variables. Actually, it's very easy to find because the marginal PDF is symmetric and the peak is at 5. So 5 is exactly the pivoting point which is going to make this whole density balance itself. So mean value of x is 5, mean values of y is 5. And for this diamond shaped region, if you find the correlation value, it comes out to be 25. And if you divide this joint density using two cuts which pass through x is equal to 5 and y is equal to 5, you are going to divide this diamond shaped region into exactly 4 smaller triangular shaped regions with areas exactly equal to each other. So when you have two areas with positive contribution with same volume of the terrain and two areas with negative contribution with the same volume of the terrain, you are going to get a covariance which is 0. So we took this example 3-4 lectures ago. We defined a flat PDF on a diamond shaped region. We found marginal densities, and then we discovered that these marginal densities represent two random variables which are not independent of each other, because the multiplication of marginal densities did not give us the original joint PDF flat over diamond region. So the two random variables were not independent of each other. That was established 2 weeks ago. Now we have found that they are uncorrelated because the positive contributions and negative contributions cancel each other out. So if there are two random variables x and y which are independent of each other, then they are uncorrelated. But it's possible for two random variables to be uncorrelated but not independent, like the case of this flat joint PDF over a diamond shaped region. You can certainly find other joint PDFs of two random variables where the two random variables are not independent of each other but they are uncorrelated. The trick is to have a joint PDF which is not defined over a rectangular or square shaped region, and have this PDF in such a way that when it is cut using two cutting partitions, the 4 parts are such a way that they cancel each other. Then you have a pair of random variables which are uncorrelated but not independent. The next example of two random variables with mutual influence is intentionally chosen as a flat PDF but in a narrow rectangular region. The narrow rectangular region has sides which are not parallel to the coordinate axis but parallel to the 45-degree angle or 135-degree angle. As you can see on the slide, this narrow strip-like region over which this flat PDF is defined is bounded by 4 lines which are shown on the slide. So when the region between these 4 lines is taken, and it is intentionally taken to be symmetric across the origin, then we have two marginal densities which are also symmetric, and they give us 0 mean values for x and y random variables. So when you have mean values of x and y 0, you can cut this joint density at the coordinate axis and get 4 regions. And as you can see from the slide, the region in the first quadrant is a long part of this rectangular strip, and similarly the region in the third quadrant is also a long part, whereas the region in the second and fourth quadrant are small triangles. The PDF is flat, but majority of it exists in the first and third quadrant, which are going to give positive contribution towards the covariance. So you can imagine what the value of the covariance for this particular joint PDF is going to be. It's going to be a large positive number, and that number comes out to be 20/3. The joint PDF was of height 1/18, bounded by 4 lines: y is equal to x minus 1, y is equal to x plus 1, y is equal to x minus 9 and y is equal to minus 9 minus x. So this rectangular shaped joint PDF, which was flat but sides not parallel to coordinate axis, gave us a positive value of covariance because majority of it was in first and third quadrant. Hence, we have a positive covariance value of 20/3. The next example of two random variables is shown on your slide, and this slide shows a joint PDF which is again a rectangular narrow strip with flat top, but this narrow strip is oriented in such a way that majority of it exists in second and fourth quadrant. So the PDF is symmetric across origin. It gives us again two marginal densities which are symmetric, giving us zero mean values for random variable x and y. Hence, the covariance is same as correlation. We are going to cut this joint PDF on the coordinate axis to get four parts. The parts in first and third quadrant are small triangular regions, and part in second and fourth quadrant are long strips. These long strips have a lot of sand volume, where sand is representing the joint PDF. So this second and fourth quadrant contributions will be negative, and as you can imagine, the covariance for this particular pair of random variables comes out to be minus 20/3. So if there are two random variables and their joint density is such that majority of it is in first and third quadrant, then the covariance is going to be a positive number. And if there are two random variables which have a joint PDF with majority of it being in second and fourth quadrant, then the covariance is going to be a negative number. We are going to use this property to find the covariance of more complicated joint densities which are not necessarily flat. They can be hill shaped or any other terrain, but you can see that if you cut this joint density at two lines which are parallel to coordinate axis and pass through the mean values of x and y, then if the majority of this sand hill is in the first and third quadrant, the covariance is going to be positive, and if majority of this sand hill is in second and fourth quadrant, then the covariance is going to be a negative number. Let's use that to find the covariance of two continuous random variables which are Gaussian, but they are not independent of each other. We talked about this type of pair of Gaussian random variables in the last lecture, and in that lecture I gave you the joint density to be multiplication of two individual Gaussian densities of the form e raised to power minus alpha x square times e raised to power minus beta y square, but there was a third term added which was e raised to power minus gamma times x y. This third term makes the whole density non-separable, so the two random variables, both Gaussian, have a joint density which cannot be separated, hence they are not independent of each other. And if you take a joint density of this form, k times e raised to power minus alpha x square into e raised to power minus beta y square times e raised to power minus or plus gamma xy, you can find the marginal densities, the mean values, the correlation, the covariance and everything. But usually this is not the format that is used in textbooks and other literature to represent two continuous random variables which are jointly Gaussian and dependent on each other. A standardized format is used to represent these densities, and that format is shown on your screen. In this standardized format, the joint density is a function of the standard deviation of random variable x, the standard deviation of random variable y, and the correlation coefficient, the end result of all the computations of covariance and standard deviations. So in the standard format, all these values are used to represent the joint density, and the expression is shown on your screen. I have used this expression to find the joint densities of a pair of Gaussian random variables which were not independent of each other. That is, the value of rho, the correlation coefficient, was non-zero. And next you can see this joint Gaussian density. This surface plot of joint density of x and y random variable clearly shows that the two random variables are not independent because the peaks of trajectories do not align themselves, as we discussed in the previous lecture. We actually intentionally made these two random variables dependent on each other by having a positive value of rho, the correlation coefficient. For this particular graph, I have used sigma x to be 1, sigma y, which is standard deviation of y, to be 4.5, and correlation coefficient of 0.85. As expected, with a positive correlation coefficient, the majority of this hill is aligned itself closer to the 45-degree line. It's not exactly 45-degree line, but it is aligned in the direction, general direction, where when it is cut on the coordinate axis or the two lines passing through the mean values, majority of it will be in the first and third quadrant. Similarly, if you take a negative value of rho, the correlation coefficient, you can generate a surface plot of a joint density which will not be aligned with a 45-degree line, but it will be closer to 135-degree line. And the next slide shows such a surface plot. And this surface plot is aligned in such a way that when it will be cut using two cuts passing through the mean values, majority of it will be in second and fourth quadrant. So if majority of the joint PDF lies in fourth and second quadrant, then essentially we have a negative correlation coefficient. In the end, to summarize what we have discussed, we extended our discussion of pair of continuous random variables which were jointly defined through a joint PDF, and we talked about their mutual influence on each other because we considered them to be not independent of each other, and their mutual influence was measured through correlation, covariance, and correlation coefficient. These three numerical measures tell us how one random variable is going to influence the other. And in the end, we saw that if the joint PDF is aligned in such a way that when it is cut through its middle part where the average values of x and y coincide, then if majority of it is in first and third quadrant, then we have a positive correlation or a correlation coefficient which lies above 0 but less than 1. And if the joint PDF is in such a way that majority of it is in the second and fourth quadrant, then we have negative correlation or a correlation coefficient which lies between 0 and -1. In coming lectures, we are going to continue with our analysis of more than one continuous random variables. We are going to transform these pairs of continuous random variables into one or two or more than two new random variables which are defined as a transformation of the two original random variables, and the transformation is not necessarily going to be a simple shift or simple scaling or a combination of shift and scaling. The transformation could be linear, non-linear, arbitrary. We are also going to cover many other interesting topics, and most of these topics will require you to be able to handle the joint PDF, which is a function of two variables, and you should be able to integrate this joint PDF and find the probabilities and other related quantities by integrating this joint PDF over arbitrary regions. Till then, I wish you the best. Thank you. Khuda Hafiz.